Afternoon, everybody. My name is Michael Fitch of the University of Surrey, and it's my pleasure to be chairing this session on non-terrestrial networks for beyond 5G and into 6G. Next slide, please. So when thinking about NTN, we've heard already it'll be an integrated part of component 6G. In previous generations, satellite's been an add-on rather than a fully integrated approach, but we imagine that 6G integration will be across terrestrial and non-terrestrial. We see that strategy, research and standards activities are gathering momentum. There's a list there of some enabling technologies and techniques just to stimulate our thinking. Quantum safe security, there's virtual function deployment, even on NTN nodes like satellite payloads. We need a three-dimensional mobility management, because now we're talking about terrestrial and non-terrestrial, so we've got height to worry about. Timing and synchronization is a big issue, to say nothing about the spectrum sharing cooperation. So today, we're actually going to look at some of the non-terrestrial use cases and some of these supporting critical technologies. The session has a technical flavor rather than the economic one, and there'll be 5 speakers. If we can go to the next slide, please, to see the agenda. 5 short talks from a very good cross-section of people. CGI, Ofcom, University of Bologna, the National Physical Laboratory, and OneWeb as a SATCOM operator. So they'll be looking at respectively use cases, 6G vision use cases, challenges and opportunities from Ofcom, critical technology enablers, resilient timing, which is very important for NTN, and lastly from the operator, the role of SATCOM as the essential component. Now, if we go according to time, we'll have some questions and discussion at the end for 15 to 20 minutes, and please, we'll respond to questions during this time. I will see the questions as they come up if you ask them on the chat in the meanwhile, but we'll address them at the end. So without further ado, I will hand the floor to Rahul from CGI to talk about vision use cases and integration challenges. Thank you, Rahul.
Thanks, Mike. Next slide, please. Hello, everyone. My name is Rahul Kataria. My fancy title is Feature Network Applications Lead, but I'm mainly a solution architect, where I work with the clients in different verticals to identify their needs and their pains, and see how the terrestrial and SATCOM hybrid network can help solve their pain. I work for CGI in the UK. We are a multinational company, about 84,000 employees, located closely to the client locations. We work in consultancy services, digital transformation. And in the UK, we do a lot of systems integration. And I work mainly in the space sector, but I support clients in multiple verticals, such as transport, energy, utilities, and finance, etc. In CGI, we are in a unique position to work with these different clients and understand what they need and what's not working for them right now in the current communications network scheme, and what they're looking for beyond 5G. What are their requirements? What are the expectations? So that's what I'm trying to cover in this session. This slide shows mainly about 6G vision. In 5G, there are 3 pillars: enhanced mobile broadband, ultra reliable low latency communications, and massive machine-to-machine communications. But I don't think 5G goes far enough in terms of the pillar. It doesn't consider many different possibilities, that not everything that needs low latency communication needs ultra reliability as well. So I think it makes sense to spread those pillars out into their own pillars. Also, 5G focuses, I mean, there are some SATCOMs elements, some non-terrestrial elements, but predominantly it focuses on terrestrial ground-based systems, and in would say a more two-dimensional aspects rather than 3-dimensional that we're going to need in future to support flying taxis and delivery drones and all those kinds of services. So extreme coverage in extreme mobility scenarios needs to be a separate pillar on its own. And not to forget climate change and our net zero commitments. So some targeted development and work needs to happen in developing low energy devices and cost saving. So that needs to be a pillar on its own. So 6G should have these 6 pillars that are shown in the slide. In terms of the KPIs, okay, it's easy. Extremify everything, 10 types everything. So the table on the right side shows the 5G, the 6G KPIs are roughly 10 times over the 5G. We can see the throughput that's changing from 10 GB per second to 100 GB per second. Traffic density is increasing, spectrum efficiency increasing, latency is coming down from 10 milliseconds to 1 millisecond. So everything is being extreme. Everything is mobile everywhere. So it's fair to say the 6G is mainly kind of network of network, everything to everything and everywhere to everywhere system. Next slide, please. Okay, so the figure on the left is kind of iterating the same thing. Is that in 6G, we need to have different layers of networks to support different connectivity options. So we have ground-based networks, then we have typical satellite networks where you have GEO, LEO, and MEO constellations. But maybe there is a need to also have another third layer, which is an aerial network, if we are to satisfy 6G latency requirements of less than a millisecond. So there's a need of a HAPS or a plane-based or drone-based, an intermediate layer that sits between the terrestrial and satellite network to provide that low latency communications. When we talk about these networks, we consider the world and the things that we can see, but there's so much to the world. We have a whole deep sea that we are not explored enough, and I'm sure we need to if we are to find the resources that all of us need. I think there's a lot of work needs to go and look for undersea exploration. Similarly, we are looking into interplanetary, maybe settling into the moon, Mars, all those things. So there's a communication network needs to be developed that allows us on the Earth to communicate to the outside world as well. So these are the different types of networks that we think we're going to need along the 6G timelines. Next slide, please. So let's look at the scenarios where 6G communication, 6G network of network connectivity is required. So let's focusing on the things that we can see and look right in front of us. So terrestrial networks. There are scenarios where we have satellite networks which works with the ground network, but there is a kind of a delay. The UE to direct UE to UE communications are not supported in 5G, and that's the holy grail. Can I use my phone or a simple device that communicates to the space network directly, and then all the traffic goes through space network directly towards another user at the other end? That's the challenge. We have a lot of Earth observation satellites flying all over the world. But if I have to request something from them, the timelines are huge. I have to request a data capture. The request goes to their payload management system. Then they command their satellite. First of all, they have to wait for the satellite to come into view so they can command it. The satellite then goes over the area. It captures the data that it needs to capture. Then it has to come in contact with another system to download the data, and it takes too long. So why can't this all be made more real time? And there could be many use cases, such as in military, such as in disaster response, where I need to request something very quickly, and I need to get the data very quickly in maybe in 10-15 minutes, so that I can make an informed decision, such as if I'm providing rescue missions in a flood situation. Can I get a map where the roads are not underwater, where I can create a path, efficient path for my rescue missions? So real-time data capture from the sensors spread all over the world is a key requirement for 6G. Similarly, if I'm able to use the in situ data that that the sensors spread all over the world, maybe on the glaciers, mountains, deserts, and sea, if I can capture that data in real time, I can create a very high fidelity digital twin of the world, and that'll help me plan a lot of disaster situations, what if scenarios, keep an eye on the what's happening on the world, keep a pulse on that, and that will help solve our problems. Outer space exploration, so there's a lot of interest in space tourism, mining other planets, because we are running out of resources. So all those systems need connectivity, and those systems need connectivity locally on those planets and connectivity to us. So that needs looking into. And the final thing is the deep sea exploration. I'm not a fan. I mean, given our past history of how we very easily mess up the environment, but I'm a realistic that we are running out of resources on the Earth, especially the precious metal that are required for battery production and all that, and there's a lot of it on the seabed. It's going to happen soon, so it's important that if it happens, we need to make sure it happens in a highly regulated way, and we monitor what's happening on the ground in real time. So if a disaster happens, if a company is not doing what they promised to do, we can hold them to account. A lot of these exploration will happen in deep sea and hazardous waters. Maybe the commanding and controlling of that could happen from shore. So NTN networks can play a big role in setting up that network and getting that data, monitoring data out, so that we can constantly keep an eye on these. These exploration could also happen using haptic controllers, virtual in a VR mode. So yeah, having a good, reliable network and low latency network is crucial in enabling these exploration. Next slide, please. Okay, so now let's look at some challenges. If we are to support this network of networks, what problems we need to solve? The first and foremost is the cell-based architecture that's been there in 5G and throughout in the terrestrial network life is no longer valid. Now we are moving towards this constantly on the move, constantly changing cell-less architecture. It's more like a three-dimensional system, three-dimensional topology. How does the mobility management is implemented in this scenario? How is the interference management, so that a system, one network does not cause frequency interference issue with another network? It is a big problem, and that needs solving. Time synchronization. These networks are connected to each other. We have satellites flying from, let's say, OneWeb network and Starlink network, and all these different HAPs, for example. How do they avoid collision with each other, for example? So they need close synchronization. They need close choreography. They need to be able to talk to each other and autonomously. And so synchronizing these time-wise is very crucial. Let's say I'm with the metaverse and the holograms. I'm sitting remotely and in my physical world, and I'm shaking hand as my hologram with someone remotely at the other end. That synchronization between I'm shaking my hand here and my hologram shaking the hand at the other end has to be done properly. And who's providing this constant ensemble that everyone can trust? All these different networks will trust and use it as a single source of time.
You have 2 minutes, Rahul. Yeah.
It's something nearly there. And these networks are complicated networks. They are different networks managed by different parties. We can't possibly manage them manually. AI has to play a crucial role. The AI won't live in a central location or the edge. It has to be distributed throughout the network. So maybe it makes sense to have a separate plane for AI. We have control plane and user plane in 5G, but maybe in 6G we need a separate plane for AI that manages the control and the user traffic autonomously. It monitors the user behavior, it monitors the user patterns, other events, and then plans the network accordingly. And last but not least is the security. We can't forget security. How do we allow these different networks that don't trust each other to use each other's services? There needs to be some agreement, some mechanism, zero trust model, or something that needs to be agreed between different networks. As you say, we're going to be using AI for security and monitoring, but we also need to keep an eye on security. That is not we also need to keep an eye on AI so that it's not being manipulated. So it's AI for security, and security for AI is going to hand to end. We're going to be in the quantum computing world by that time. So something has to be done to make sure the communication links are quantum secure. These quantum secure keys need to be distributed, and we think the NTN can play a big role in distribution of these keys. Okay, I think, yeah, next slide.
I must hurry you, Rahul.
Yeah, I think I'm done. Like, yeah, there's some references there.
Okay.
Thank you.
Thank you very much, Rahul. Interesting. Let's pass straight on to Ofcom, and Anas, you have the floor.
Thanks very much, Michael. Right, next slide, please. That's not my slides. Right, some technical challenges.
Yes, I think maybe Alex is having trouble finding the slides that Anas sent in. Anas, do you have the slides that?
Yeah, there you
Okay.
are.
Yeah, wonderful.
Thanks, Alex. So, hi everyone. I'm Anas Rawi. I'm part of the emerging technology team, which actually has been renamed recently to Communications and Media Technology. The team in Ofcom, we see the evolution in mobile networks, that's 5G, 5G Advanced, all the way to 6G, and with the integration of satellite communications or non-terrestrial networks, vital infrastructure for the consumers and businesses in the UK. And the remit of our team really is to track and anticipate emerging trends in technology, and make sure that we communicate and collaborate with the external stakeholders and work with the rest of our colleagues in Ofcom across the various groups to make sure that the innovation cycle is as smooth as possible, and there are no mismatches between emerging technology and regulations. And with that, I will pass to the next slide, please, Alex. So probably before I start talking about the requirements and the challenges of all the opportunities for non-terrestrial networks, I'll just touch on the background of satellite communications. If we look back at 1945, we will find that Arthur Clarke was actually motivated by two factors. There's the economic argument. Actually, you can cover the entire globe with two satellites, given that you position them at the correct distance in the geo orbit. And then there's the second argument, which is the availability of enabling technology. So at the time, Clarke predicted that the rocket technology is on a track to evolve, so it becomes a viable solution to launch these satellites in orbit, and also the solar engines that were available. So really, the economic argument and the enabling technology, this is what motivated satellite communications almost 80 years ago, and still these arguments still hold today. And if we think about the terrestrial network, it has its own limitations. So you can't really push the terrestrial network everywhere, but actually terrestrial network, you can get that global coverage. And there's this there's this complementing role between the two networks. And next slide. Probably in the interest of time, I will skip this slide as well. Next slide. Yeah. So the role of satellite communications. Yeah, it's probably most of the audience know what are the key applications for satellites: positioning, navigation, and timing, broadcast services, broadband services, Earth observations, emergency services, and also emerging IoT. And if we think about the inclusion of non-terrestrial networks in 6G, it actually starts with 5G, which 5G in a few years' time would have been mature enough to deliver most of these services with release 18 and onwards with 5G Advanced. However, to integrate the two networks, we need to pay close attention to various design aspects, requirements, specifications spanning the transport backhaul, front haul, the terminal design, and also the services. All the design specifications governing the terrestrial network, it needs to be adjusted, and so that there is that harmonized integration between the terrestrial and non-terrestrial. And I will start with the synchronization in telecommunication, which is on the next slide. Alex, please. So synchronization in telecoms is vital, whether it's time, frequency, phase. You can't really run the telecom network without synchronization. And again, the requirements on synchronization is very much network architecture dependent, service dependent, technology dependent. For everything you want to do in the network, there is a very strict requirements that you need to follow. And if we take, for example, 5G, so you get the signal, for example, of a GNSS source, and then this goes through a chain, goes through various segments in the network, but in every segment you need to be able to calibrate and make sure that you're within a very tight margin. And if we look at 5G, for example, in the next slide, requirements can be anything between 3 microseconds all the way down to 65 nanoseconds. These are very stringent requirements. And if we are going to think about the use of satellite to transport timing, we need to make sure, or need to understand what are the implications, what are the limitations, and what is feasible, what are the feasible requirements that we can actually implement with non-terrestrial network. Because, for example, if you have a cluster of RUs, and you are using carrier aggregation and so on, the requirements between these multiple RUs need to be down to 130 nanoseconds. And if you have microcells, for example, then you need 3 microseconds. Otherwise, you will end up with interference between these two G0Bs or base stations. And it's quite important that you get the most out of the spectrum, because we have a limited spectrum. So all these requirements need to really fully absorbed, and then you project it into the non-terrestrial network, and then see what is feasible and what's not feasible, and where do we need to adjust the design specifications. Next slide. So if we look at the status of non-terrestrial networks in 3GPP release 17, the non-terrestrial network sits basically between the G0B and the user terminal, and there are very specific requirements and specifications to support this integration between the 5G and the non-terrestrial network. So, for example, the payload has to be completely transparent. It supports only 5G frequency division duplexing. The terminals, for example, needs to be GNSS compatible. And the primary focus here, or the primary goal here, is to extend the coverage of 5G. So it's complementing the terrestrial network by extending that reach from the 5G towards remote end users. And if we think now about bringing that satellite network deeper in the NGRN, the next generation radio access network, then we need to think about the synchronization aspects that we've just discussed on the previous slides. Can we actually calibrate out all the interfaces in the satellite network so we can come down to a precision of 130 nanoseconds or 260 nanoseconds or whatever the number is? And also in terms of latency, because you have a latency budget, you have a signal budget, and then we need to make sure that this is reflected on the applications as well. So you probably need to tweak the quality of service requirements for various applications. And the next slide. So future of satellite communications, and I can't really put it better than Raul. He gave a very aspirational vision for non-terrestrial networks. But these are the key features, in my opinion. So the advancement in phase array is emerging across all the satellite segments, whether it's the ground segment or the space segment or the user segment. Regenerative payloads. Basically, you have the G0 be in orbit, and you have the flexibility to do routing in the orbit. It gives you more degrees of freedom. You reduce the latency rather than routing the traffic, getting the traffic off the orbit down to the terrestrial network. So these are the key emerging, let's say, features in non-terrestrial networks. And also, of course, you have the cloud native nowadays is emerging in that's the direction of travel, because it gives you that programmability and the flexibility in the network design and delivery of applications. And of course, coordinating spectrum. You need to optimize this spectrum because we have a limited resource, and my esteemed colleague Elizabeth Quintana will talk about this. In terms of key challenges, if we want to integrate the non-terrestrial with the terrestrial, at the moment, the terrestrial is multi-carrier. So if you think about multi-carrier in non-terrestrial, you need to pay attention to Doppler, especially when we're thinking about low Earth orbit and high mobility scenarios. Also, the latency, again, that I mentioned earlier. So you can easily get a latency in excess of 30 milliseconds. And I think I'll stop here because I need to give time for my colleague Elizabeth to talk about her slides as well. Thank you.
Thank you, Anas. Yes, so the presentation of comes in two parts. So now we have Elizabeth Quintana, whose spectrum and regulation is her speciality. Thank you, Elizabeth.
Thank you, Mike. Thank you, everybody. Delighted to give you a few more thoughts from Ofcom. Ofcom, as Anas mentioned, is the UK's telecommunications, media, postal and online regulator. So we are increasingly busy across an increasing number of areas. And what I wanted to do was take a very, very stratospheric view of some of the areas that we're thinking about in the Spectrum Group, about spectrum both for future mobile and also for satellites as well. If we can go on to the next slide, please. Brilliant, thank you. So we published last year an update to our broader spectrum management strategy. As you might have noticed, there are a wider, ever-widening range of sectors who are interested in developing wireless services, and this is making our life extremely interesting. So we are aiming to do more to support wireless innovation, both to help UK companies and others wanting to operate in the UK to understand how to engage with us, but also to think about ways in which we might be able to get them access to spectrum where appropriate. We are doing more to license locally, and we're doing more to promote spectrum sharing, so that whereas before different services had very clearly defined spectrum bands that they could operate in, now, because all services are looking to expand the spectrum that they have access to, and there are more ways in which services are integrating, it is more appropriate to see if we can share that spectrum. So we set that out both in the spectrum strategy and in our spectrum roadmap, which showed how we were going to implement it. And I would recommend both of those documents if you want to find out more. Next slide, please. So we also published a document earlier this year looking at the future of mobile, and we noted the progression that mobile has made over the last 40 or so years. And we outlined some of the potential features as 6G. Mike, can you keep clicking through on this slide? So as you can see, some of those potential features are areas in which we can immediately see satellite services would play a role. And Rahul did well to point out that, you know, it is not just communications from space that's going to be important going forwards, or those Earth observation satellites on which we depend for our weather forecasting, but other Earth sensing and atmospheric sensing will be very important to a range of services going forwards. But as we all know, satellites can provide global coverage really easily, and there are a number of unique use cases that only satellites can deliver, and so it certainly makes sense that satellites would be integrated more closely with terrestrial networks going forwards. Next slide, please. So it's always interesting to go back to the data, and again, our discussion paper in March looked at projected data traffic in the 2030s and beyond, so when we're starting to talk about 6G coming online. My colleagues came up with 3 scenarios, and the lower and the upper limits are definitely the outer edges of where we think the data might go, but we're looking at between 7 and 52 times the data that's currently going through our mobile networks, which is always slightly mind-blowing. Oh, thank you. So I guess the question here with these non-terrestrial networks and satellites is how much of that data are we expecting to pass over satellite? And what does that mean in terms of how many satellites collectively will we need to have in space? What sorts of frequencies are they likely to be operating on? What types of services are they looking to deliver, and what they will be using both for the user terminals but also for the backhaul. And again, going back to Rahul's points on the Earth observation, there were some very interesting discussions at the last World Radio Communications Conference at the ITU and at the UN about, you know, the development of 5G, but also the need to protect certain frequencies, because that's what we use to detect water moisture in the air. And I think we can all agree that accurate weather forecasting is something that we all will rely on with climate change. So the need to for particular services to have access to particular spectrum will remain important. Next slide, please. Along with how will satellites develop, we also need to understand how terrestrial networks will develop. Looks like there are going to be more dense networks, an increasing number of players, greater deployment of private mobile networks, more spectrum sharing, the integration with other networks, which we're here to talk about, and also much more cloud and edge computing. And again, even when you look at geostationary satellites, which people tend to focus on less, once you combine that with edge computing, then it gives you some additional features as well. As undoubtedly there will be new spectrum requirements. I think the interesting thing here is discussions that are starting to merge about so-called mid-band spectrum between 7 and 20. So for those in the satellite community, some of those are quite key bands for broadband services, and also interest in terahertz for backhaul for mobile networks. Again, for the Earth observation community, there are some frequencies that are quite important. Some of these could be shared in the future. We just need to understand better if and how that can be done. And technology is changing all the time, so we need to keep abreast of that. Next slide, please. Thank you. And So we have also been thinking a lot about the changing satellite and space community, and again, thanks to Rahul for pointing out some of the wide-ranging different satellite services and space services that are coming along. Here I've got a slide about satellite communications. We're also considering Earth observation, space launch, position navigation and timing, lunar communications, a whole range of different spectrum uses, which is just brilliant, makes my job lots of fun. Here, sorry, Mike, can you click once more? The thing I wanted to point out is we're just monitoring a really interesting development in technology, looking at whether or not satellites might be able to provide base stations in the sky effectively, so connecting mobile handsets that are unmodified, which is definitely a non-trivial task. So clearly, as a regulator, we would be very keen on anything that can expand coverage, that would enable greater spectrum sharing, but we will just have to see how the technology develops. And as we said more broadly in our space spectrum strategy, we're aware that a lot of these services are being delivered by these constellations of satellites in low Earth orbit and medium Earth orbit. And again, we are very much in favour of those, and we're looking to enable them. However, they are more dynamic, they do pose some additional spectrum challenges, and they will need to coexist with other services. So we are watching all of that, and we are preparing ourselves, whether through our national regulations or in how we engage internationally with our partners or our counterparts, but also at the ITU and at European bodies, to discuss and understand how we might need to change regulations to help some of these things to come to fruition. So with that, happy to take questions on any of those at the end. I'll hand back to Mike. Thank you.
Okay, thank you very much. It's interesting always to get perspective from regulators, from Ofcom, and I'm sure we'll come back to questions later. Alessandro, we need to push on with time's getting a bit tight here, so we need to move on. Alessandro, the floor is yours to talk about critical enabling technologies.
Thank you very much. Okay, good afternoon, everyone. So my name is Alessandro Vanelli Coralli, and I'm from University of Bologna in Italy. Next slide, please. So I just have one slide on the role of NTN in 6G. You have already heard by a previous speaker. So essentially, we know that 6G will be much more than just extremely fast connectivity. It will be the convergence of mainly three worlds: physical, digital, and human. And so we need to have an infrastructure able to support this type of new paradigm. So non-terrestrial network will be important, fundamental in this, in order to provide ubiquitous, continuous, flexible, and resilient infrastructure for several, let's say, directed connectivity to smartphone, in outdoor, but also in light indoor, and in vehicle, for example, for emergency communication, for low data rate. Connectivity to mobile platforms like trains, planes, ships, drones, high altitude platforms, where in particular drones and high altitude platforms operates both as element of the network themselves connected to the network, but also as final user of the network, so as user equipment. We don't have to forget the broadcast and multicast capability of satellites. So this is another element that has to be included in the non-terrestrial perspective. Low latency communication in support of vertical markets like railway application, automotive, aeronautical, and so on. And network-based positioning, which is very important, in particular, in order to allow not only the positioning, but also the timing that we were talking before. So there's a lot of ongoing under the head of positioning-based networking. Sorry, network-based positioning. And then IoT application, massive IoT. So next slide, please. So in this perspective, the path from 5G to 6G of the NTN has been already pointed out, but it's pretty clear. In 5G, in the current release 17 just completed, we talk about integration. So we built essentially an NTN component on the basis of something that was already designed for the terrestrial part. 5G advanced, let's say release 18, 19, and 20 will actually see the introduction of enhancement with additional capabilities, increased performance, and the deeper integration of NTN into the 5G ecosystem. But 6G will actually have to change the paradigm, and NTN should be actually fully unified. I will not say integrated, but fully unified at infrastructure level, on the basis of what we already see, a 3D or whatever, a multidimensional, multi-layer architecture, where you have different nodes flying at different altitudes, but they are interconnected. So you have geostationary satellite or even elliptical orbit satellite interconnected with lower orbits like MEO or LEO or even VLEO, drones and apps in a continuum of communication which opens a lot of challenges in terms of routing in the space, in terms of configuration of the infrastructure and so on. But that will allow to see the NTN component as another component of the entire ecosystem, so with no different with the terrestrial one. So next slide, please. In this perspective, the KPIs that we need to target in terms of the NTN 6G infrastructure are quite clear and already somehow touched before. We have the latency, which shall go essentially 5 times lower than what we have currently in 5G, so below 10 milliseconds. The positioning provided by the NTN infrastructure, not by the GNSS, with a 10 times improvement with respect to the current status, so less than 10 centimeters of accuracy. Data rates that shall be above 5 times what we currently have in 5G. For example, for ultra small terminals and VSAT aperture terminals, something like 1.6 gigabit per second on a 400 megahertz bandwidth. And for the handset, direct connectivity up to 20 megabit per second on the 5 megahertz bandwidth for direct connectivity from the NTN. And then we have this new capabilities, new KPI, which is the light indoor and in-vehicle connectivity, which is actually something completely new with respect to the classical satellite communication that can be achieved by exploiting the multi-carrier characteristic of the waveform for the low data rate, for example, for emergency communication, very short messages in emergency communication in indoor or light indoor. So this actually calls for several building blocks of what we call enabling technologies that we can actually try to group under several headings, starting from the architecture and the system design. The multi-layer constellation needs to be designed from geo to drones with innovative LEO and VLEO constellation, in particular, maybe at few different altitudes in order to avoid crossing over the poles and so on, and also to minimize the cost of the launching and the maintaining of the constellation. Optical inter and intra-nodes links, which means the connection between the nodes at different altitudes, inter-segment, or at the same altitude, intra-segment. Cell-free MIMO. So we need to go beyond what the current geographical coverage, and we go to cell-free and traffic-driven coverage. In network, and we put the emphasis on edge computing and communication. Softwareization, virtualization, and orchestration is something that needs to be implemented in order to disaggregate the system and open the market and to new players. To avoid to stay in the same cage where we are. This is a key element, not only from the performance point of view, but also for the market perspective. Advanced IP, as I said, routing in the sky, resource management which is a very challenging element because of the complexity of the network. And least but not last, integrated edge communication and computing. In the sky, essentially, this is something that we need to target. We have regenerative payload. We need to bring there the computational capabilities and the storage capability. The waveform is not unified, will not be unified, will be a flexible and integrated with the common numerology, but specifically designed for the NTN case, the NTN scenarios, which is pretty different with respect to the terrestrial one. We cannot think of unified waveform, but an integrated one with the same numerology and flexible reconfiguration. Dynamic spectrum access and new spectrum. This is a key point in a so complex and unified architecture. So coordinated and uncoordinated sharing among different access technologies and among segments between the terrestrial and the NTN one. We will see a couple of slides on this taken from a recent project funded by EC. And also higher frequency, not only QAV, but above also those frequencies in order to find more spectrum to satisfy the high data rate needs of the new application. As I said, positioning is a key element, is a key enabler, network-based, so independent of the GNSS. Currently, we know that most of the NTN work carried out at 3GPP level assume the GNSS at the receiver in order to compensate the Doppler of the low Earth orbit constellation, pre-compensate the delay. This is based on the presence of GNSS. Network-based positioning will allow to avoid this dependency. And then, as we have heard with the very first presentation, artificial intelligence at all levels, from the orchestration of the resources to the orchestration of the entire infrastructure, you need actually to configure the infrastructure in order to provide the service that is requested by the orchestrator. So we have two levels of orchestration in here, but also the AI at physical layer, down to the physical layer, with a lot of emphasis on how to exchange the models, how to exchange the data in the sky, how distributed AI can be used or federated AI can be used in this type of constellation. And last but not least, antennas and components. Active antennas are very important in here for link budget and in particular for flexible coverage in order to go towards a cell-free approach. Reflecting surfaces also important for indoor coverage at larger bandwidth. Regenerative payload, this is a key element, but this needs to be supported by the development of hardware, of platform that are capable of high parallel computed, but very efficient in energy consumption. And last but not least, again, optical devices in order to support inter-node links. So if we can go to the next slide, I will actually want to introduce a couple of examples related to cell-free on one side and dynamic spectrum allocation and coexistence. So next slide. This is essentially the case of multi-point transmission. So this is cell-free MIMO with multiple satellites transmitting from the space. Essentially, you know that 3GPP foresees two types of coverage, one with Earth moving beams, essentially no beam steering, and the other one on the right, bottom right, Earth fixed beam, where you actually move and steer the beam in order to keep the coverage. So essentially, you can think that in a mega constellation, or not only mega constellation, but also incomplete constellation, but with high density of satellite on the same areas, for example, for IoT application that are no time sensitive, the UE is invisibility of multiple satellites. So you can actually start transmitting from multiple satellites as in a comp for terrestrial approach in order to improve either the throughput or the availability of the link in suburban areas. or in non-line of sight approaches due to obstacle. So essentially, if you go to the next slide, you can see here different curves that you can actually look at.
I need to rush you, Alessandro, sorry.
I'm done. What we achieve here, what we can see is that transmitting from multiple satellites actually increase the availability of the link, keeping the throughput of the system. On the next slide, what we actually see is an example of non-coordinated spectrum sharing between terrestrial and non-terrestrial. So I want to point your attention on the coverage picture, the black and white, where you see in black the terrestrial coverage, and in blue, sorry, not black and white, blue and black. In blue, the satellite coverage. You see that the terrestrial coverage in the second and third case, which are limited and controlled for the interference, is not reduced, but the satellite coverage is increased, which means that the two systems can actually coexist in a non-coordinated way. So it's only the satellite that tends to reduce the interference produced on the terrestrial one, with no impact on the terrestrial interference to noise ratio. On the next slide, you see the case of coordinated case where the 3GPP frame structure is used in order to assign resource blocks of frequency to the satellite and frequencies to the terrestrial in a coordinate way. What is happening is that the spectral efficiency that you see here of the terrestrial case is not impacted, whereas the satellite capacity actually per cell increases well beyond 1.5 or 2 bits per second per earth. So again, also in coordinated case, there's a gain that is possible. So it's very important to go in this direction. Next slide, in order to conclude. So what I just wanted to highlight is that I actually listed a series of technology, of building blocks that are very critical in terms of being able of developing an NTN infrastructure unified with the terrestrial one. Not integrated, unified. The integrated one was actually something that we already have in the 5G. We need to go beyond that one. This is a long path that we took many years ago. We started this with this activity of trying to include satellite into wireless system at the beginning of 2000. I saw in the participant, Professor Barry Evans, we started together. Well, he started with a project in 2000. There's been a long path to get to this way. Now we really go, and we really shall go for a fully integrated, unified infrastructure. And that's all from my side. I think I stayed in my 10 minutes.
Yes, thank you. Yeah, just about. Thank you, Alessandro. Yeah, unified, not integrated. Yes, next step. Yeah, indeed. Very interesting. We have a bit of a different talk next from National Physical Laboratory, Dan Veal, about timing, reference timing. So Dan, the floor is yours for the next 12 minutes.
Afternoon, everyone. Go to the first content slide. So I come from the National Physical Laboratory in the UK, which is the UK's national measurement institute. The reason that's relevant is I'm not a telecoms person, but we hold and manage the UK's timescale. So we take a bit of a step back. We talk about timing, synchronization, etc. in telecoms as a kind of a utility that's used in telecoms. So UTC, which we all have kind of heard of, is universal coordinate time. That is the time scale which is agreed worldwide. So no matter what system, what network, whatever, you should all reference back to there if you want to be linked to the rest of the world. That's actually composed as an average time from about 80 national institutes. And it's back calculated, which is a bit weird. So it exists as something you can check every month and say a realization was off by X nanoseconds. So how does it actually get implemented? It's implemented by the contributing institutes. If you go to the next slide, you have to have an instance of UTC. So of all the organizations on that map, you can get instances where you can actually have a feed, which is a time signal, which is traceable back to UTC, this kind of average measurement. So if you look on the east coast of the US, you see one of those on there is called USNO. That is the source of GPS time, the US Naval Observatory. So the worldwide sort of coordinated average of these times, an instance realized on the east coast of the US is what feeds the GPS constellation, which is one of the absolute, overwhelmingly major sources of time. So if you go to the next slide, the reason I bring that up is that as infrastructure providers of critical infrastructure, it's really important that anyone working on a non-terrestrial network is aware of the big dependence. So within UK government, to give you an example, there have been a number of documents in the last several years. So on the left-hand side, Telecoms Diversification Task Force, Lord Livingston, talking about one of the key items in there was the timing supply chain, MPL was mentioned in there. In the middle, there was a London Economics report, which was focused on GNSS time, but the impact of GNSS going down in the UK was on the order of £1 billion a day. Again, think of the impact of having a critical resource like comms, which is based on ground stations, infrastructure all over the world, that all points back to a number of GNSS constellations. UK National Risk Register, and on the right-hand side, something called the Blacker Report. So next slide, please. This is a report from circa 2017 that got a lot of traction in UK government because it pointed out that there was a huge dependency of critical national infrastructure, so things like the water system, telecoms, finance, etc., on timing in particular, and that being an issue if the overwhelming majority of timing in some form or fashion comes from GNSS like GPS. So some of the use cases, the red boxes were clearly telecom space, but let's say the core technology telecom space. But I'd like to point out a lot of the use cases are exactly the use cases that we all want to enable via 5G, 6G, non-terrestrial networks. So timing ends up being a really massive worry for government to make sure that provision of timing, criticality of timing isn't effectively a threat to national infrastructure in various different ways. We go one slide more, just pointing out again this government report that again within the UK got a lot of traction, a lot of recommendations specifically around CNI, critical national infrastructure operators, about reporting dependencies to government, about making sure that they have adequate provisions in place. So again, good practice, nothing new, but it's just give you a bit of a picture of how much timing is actually thought about within government in the context of other things. You go one slide further, please. A few considerations. This won't take very long. So I've already pointed out GNSS is overwhelmingly the source of UTC, a realization of UTC for things like critical national infrastructure, like telecoms, non-terrestrial networks. So you should all be thinking there's a huge dependence for a non-terrestrial network on GNSS. You kind of think about the path. You have this worldwide timescale realized in GPS, for example, the east coast of the US, goes up to a constellation, beamed down to networks of ground systems, back up to non-terrestrial network satellites, back down to users with an interface with other things. So you start thinking about the paths and all the things that could go wrong in terms of where the timing is derived, where timing is being put to the system. So ground stations, satellites, the power grid that feeds it. It starts being quite complex. So I just sort of point this out as saying these are really important things to think about because time is not just sort of an easy thing to fix where you just have a certain accuracy. As long as it's an accuracy, that's fine. And I'll just point out, selfishly, one of the things that's happening at the moment is countries are realizing that deploying instances of time. So in the UK, for example, MPL being the guardian of a UK time, we have a large program that we run, which is looking at ground infrastructure that would feed all kinds of other national infrastructure, such as base stations for non-terrestrial networks and ground-based telecoms, space-based telecoms, so that there is diversity of supply, so that there is more resilient time available. If you go one slide, please. And maybe point out interoperability is so important there. So time being especially tapped in different countries, different infrastructure, different networks, it all has to be traceable, and you have to pay a lot of attention to where the traceability chains come from. Some of the slides are a bit slow, so I'm assuming you've got one called National Timing Center Program. The National Planning Centre programme is something we run, which is basically within the UK, setting up a network box, providing innovation opportunities for UK companies and looking at skills shortage. I just sort of say that as an example of the sort of ground-based things that need to be done to help properly feed the infrastructure that will go into non-terrestrial networks. Last slide, the next one then, please. Just the last thing to point out, 5G and 6G is perhaps it's obvious, but it's both a user and a provider of time. When I say users, it's a consumer. So it needs good, accurate, resilient, etc. timing to run the infrastructure for an example, non-terrestrial network. So there are all kinds of things that need to be considered. Again, dependence on GNSS as timing source, jamming, spoofing, clock errors, multipath, all the sort of stuff that is quite common to know. Building resilience by diversity, really, really important. Again, that's why I point out the role of things like national labs in different countries and paying quite a lot of attention to the sort of things, multi-constellation receivers, holdovers that need to be built into these networks, both the ground and the space segments, to ensure that there is resilience. And then thinking about the traceability of all the distribution mechanisms, much more complex. You know, getting time from the data center ultimately will be traceable back to UTC, but the path it takes, may not be obvious. And then obviously the flip side, timing of 5G, 6G, NTN as a timing provider. That's obviously the reason these infrastructure exists is to provide distribution of data, time, etc. But that has a whole other complex thing, because if you're providing, let's say, a timing and position signal via a 6G future infrastructure, it becomes very important to have the traceability right, not just so that the system is coherent and it's got a sync which allows it to run, but such that anyone picking up time, maybe on a mobile platform, is able to get time from another source, maybe a ground-based 6G network, or maybe a direct GNSS feed, or maybe some other RF broadcast as an example, so that they can run their use case knowing that there's proper traceability from any other sources of timing. So hopefully that was useful, a little bit of a different take on timing and the importance of it, and I will hand back to Mike.
Thank you, Dan. Very interesting. Yes, something that's not considered enough. So thank you for that. We now turn to Ben Allen from OneWeb, a real-life satellite operator, for an interesting take from the operator viewpoint. Ben, the floor is yours.
Yes, good afternoon. Good morning, everybody. I'm just arranging my screen sharing here. Bear with me 1 minute. Hopefully you can all see that. My name is Ben Allen, and I'm Director of System Modelling at OneWeb and Visiting Professor at University of Surrey. I have a talk really based in 3 main parts: an introduction to OneWeb, a short video clip, which is a virtual demo, and then a couple of slides on 6G itself and the role of LEO satcoms in the world of 6G. So in case you don't know, OneWeb is an end-to-end communication system based on a fairly large constellation of LEO satellites. We currently have more than 400 in orbit, and a number of Earth stations in relation to that. And we're anticipating full coverage of the Earth by around 2023. The system looks something like this, whereby we have a number of gateways, an operating center which holds everything together. Then there are a number of POPs, or points of presence around the world, which is where the OneWeb network joins the rest of the internet or users, deployment partners around the world. There's the satellites in space. Eventually we'll have around 600 in space on a 1,200 kilometer orbit, including a number of spares. And they would be serving things like connectivity to airplanes, ships, trains and railways, offices and homes, cars, etc. So those are some of the verticals that we serve. We have prime spectrum in the KU and KA band, KU band for the user link and the KA bands for the feeder link. And achieved latency is well below 100 milliseconds, and terminal download speed currently of up to 195 megabits per second. So this is a short video which I am hoping yes, I should be sharing sound, hopefully. So I'm just double checking that the sound was coming through. This is about a 3-minute video which shows a virtual experiment. Just to give you the context, this took place just a little more than a year ago. So there were far less satellites then in orbit than there are now. We've had something like 9 or 10 launches since then. So there are more planes and more satellites. This is a relatively early experiment, but it has a nice, there's a little bit of sort of marketing in there, but actually there's a nice bit of technical awareness too, and technical content, which is why I thought I'll play it. And then we can say a little bit more about 6G.
OneWeb is a global network of satellites that cover the whole Earth, connecting everyone, everywhere. We're here in Melbourne, Florida to show an early pilot of our satellite network, and we're going to connect our user terminal to the satellite network and back down to Earth so that our customers can see the speed and the low latency and the maturity of our network. This is our gateway antenna. So this antenna is talking to our spacecraft, our fleet of spacecraft as they move overhead, and then talking to literally hundreds of user terminals. So it's connecting the data from the internet, from the cloud, over our satellite network and to our end users and their user terminals. So this antenna is pushing hundreds of megabits per second of data out.
Here we are connecting to the OneWeb satellite on this orbit. So here we have the 95, the satellite number 95, which go over Florida, where we are connected.
Very confident about this one.
Yeah, it's going quite well. The SNR are good, and the data rate seems very good. So perfect. Yeah, the SNR is a receive the ratio between the signal receive and the noise at the terminal side. So this is a metric that we are using to assess the quality of the communication. So here we have around 15 dB SNR, which is very good. And we managed to get 500 megabit there.
Wow! That's great.
So yeah, we can ping there.
Ping session running here. So 32 is
39, 36.
Yeah, 37. Yeah, you can show.
Last time you made 27.
Here we go. I can kind of share the screen. You can ping it yourself in the thing. So I think what's really key here is that, like, I can see you guys speaking, and the sound is complete. The latency tells the story here, right? This is perfect.
Here you can see that there is two antenna, Ntn antenna, which are tracking our satellite and switching from one satellite to another when there is handover.
Seeing here is every couple of minutes we hand over, every 11 seconds we're handing over beams, every few minutes we're handing over satellites, but there's no impact on the team session, right? There's no pixelation, there's no jitter. Perfect.
So that's an introduction to OneWeb, and then showing a demonstration of our real system of real satellites, real ground network, and some connectivity going over it, which was demonstration of pretty low latency, and high data rates, etc. So that's today, or at least that was a year ago, and we've moved on about more than a year since then. I'm moving on very rapidly. So before we know it, we'll be in the world of 6G. But so what? Why would we care? What is driving 6G? And what has brought us together for this session this afternoon? And here are some ideas that I've put on the screen as to what might well be driving the future. And so there's the metaverse, for example, which we probably very well have all heard of, and really demanding more connectivity for more people at any time and anywhere. And not more screen time, but more higher quality screen time. So that could mean higher resolution, 3D graphics, the tactile internet with haptics, fully immersive with augmented and virtual reality, but really importantly, interoperable security and privacy, maybe immersive gaming as a massive driver, and all the things that go with that in terms of latency, data, etc. And a successor to Teams in the professional world. So at the moment we're on something like a Teams call on Zoom or whatever platform you're using, but to succeed that in a new world of what that could be. What about sensing? So being able to mix radio communications and sensing together, more sensors, different sensors, also driving things around positioning and timing, etc. And then also, really importantly, the quantum watershed. So what impact will quantum computers have in decryption, and how can we harden our system against that, being able to detect interceptors and making sure that we have trust and authentication in place. So to deliver all this, we really need next non-terrestrial networks and terrestrial networks to be able to work together in order to achieve a fully global rollout of some of these drivers. So again, what would the role of SATCOMs be in this, or specifically maybe LEO satellites in terms of OneWeb? So enabling a network of networks to be able to reach global coverage and really helping to close the digital divide, to assist the metaverse and all the user cases that the metaverse brings, providing robust end-to-end security, privacy and trust, and capacity provision. So more users demanding more capacity and helping to deliver that, and providing a global low latency, but even especially when that's cache assisted. So to bring the latency down from the few tens of milliseconds that we have in today's network, but making sure that that's cache assisted. So what do we need? We need higher resolution network timing and synchronization, new spectrum, spectrally efficient waveforms, really important interference management, and that could be technical, it could be regulation, it could be both, and spectrum sharing and a supportive regulatory environment. We need regulation and standards, influence and interoperability from the terrestrial and the non-terrestrial world to work interoperably, and network interfaces to support that, and fit for purpose protocols such as routing, handover, end-to-end quality service and so on, and integration with a range of user devices, so whatever those user devices might be, to be able to integrate with them, whether it's direct to user devices or indirect, and making sure that end-to-end integration is in place. Well, importantly, from a space perspective, we need to have a choice of orbits and launches to support it. No launches, and it really is nothing to talk about. So that's an absolute vital bottleneck to be aware of. And not forgetting responsible space. So all the space debris, junk, etc., that disused satellites that is growing, and making sure that we do take that seriously and responsibly. And really the second to last point I wanted to really just put out there, maybe it's slightly provocative, but what about an open standard for 6G to support non-terrestrial networks, and make that an open standard, much like the discussion around Open RAN and 5G for terrestrial networks. But what about an open standard? I've deliberately put a question mark after that, but above and beyond anything else, viable economics and a viable business model, because if you don't have that and no launches, etc., then there is really nothing more to be said. So that's my lot, and thank you very much.
Okay, thank you. So that's the end of the presentations. Thank you, guys. We've actually run very close to the end of the session. we've got time for one question, which has come in from the audience, anonymous question, which is there going to be enough power in the satellite payloads to support all this new sort of processing going on, especially in small satellites? Who would like to take it? Does anybody? Because we got 2 minutes to answer the question, and then I think it's the end of the session. So, yep.
Well, maybe that's one for for OneWeb, since we have satellites up there right now. And the answer is yes, I get it. And good question. And maybe having more satellites to distribute the load between more satellites is one thing. Maybe carefully designed payloads is another. Maybe reducing the reliance on payloads and having things that are more ground-based another. But the quick question is, yes, power is really, really important, and modeling and understanding and working within the power limit is absolutely vital. And maybe there's a breakthrough to be made in terms of solar panel efficiency, whether that's hit physical limits, or there are new technologies coming through that could perhaps double or triple or even quadruple the efficiency of solar panels. Would be huge, not just for space, but obviously for generating electricity on the ground as well.
Sure. Okay. Good. Any final comments from any of our speakers before we close the curtains on this very interesting session? No. Okay. We've only been given 1 minute's grace, so I think we better end the session there. Thanks very much, guys. Very interesting. Lots of information. I'm sure there'll be lots of follow-up, and we look forward to doing it again next year, perhaps.